Okay, brilliant. Sorry about that, some technical problems. Thank you for coming to our seminar. So we are Stat Central. We are the statistical consulting unit at the university. We're here to help you with your stats. So if you are HDR students or PhD or Masters by Research or staff at the university, please get in contact with us for study design, analysis, contracts, and anything statistical. We can either help you or direct you to somewhere who can. Today, we've got Peter Humburg talking to you about multicollinearity, which is one of those niggly things when you fit linear models. And he's going to tell you all about it. Okay.
Thanks, Gardana. I hope we won't have any more technical problems. Let me just hide this. And then we can get going. Yeah, so welcome. Thank you all for coming. It's great to see people online and in person. And yeah, so I'm here today to talk to you about multicollinearity, which is a little bit of a troublesome topic. When we talk about linear regression, we often talk about the various assumptions that we are making and that we probably should be checking before we put any sort of weight on our results. And some of these we talk a lot about, and some of them maybe not so much. So, we know there should be like a linear relationship between your predictors and your outcome bar. That's it's a regression, and then we have some assumptions about homogeneity of variance, and we can check this with residual plots. And if you don't know about that, then you should go and watch Gardana's seminar from September, I think, where she explained all of that, and everyone who attended was an expert in reading these plots afterwards. So go and check that out, but not right now, because right now I want you to listen to me, hopefully. And we also know with linear regression, our residuals should be normally distributed, and we look at QQ plots to check those. And you can similarly become quite proficient at sort of reading those and deciding whether this looks fine or not. Well, there's this other thing with linear regression, is that you shouldn't really have multicollinearity. And we tend to talk about that less frequently, I find. So I thought, since Gardana talked about these other wonderful things last time, I'll try and talk a bit about multicollinearity today, so we can complete the picture a little bit. And well, so the first question naturally is, what is multicollinearity anyway? And it's not pairwise correlation, right? And on the occasions where we do talk about multicollinearity, I often do see people do that, right? So you might be aware that you do need to check for multicollinearity because it can cause trouble. And then what some people do is they go and look at pairwise correlations between their predictors. And then either these are high or not. And if they're high, then you avoid. And if not, then everything's fine. Right? And you shouldn't really do that, because multicollinearity is not the same as pairwise correlation. So this is not a good way to check. What it is correlation between a predictor and a linear combination of the other predictors in the model. Right? So this is not just two variables, it can be lots of variables, depending on how complex your model is. And specifically, we are talking about the predictors in your model, not just any variables, just the predictors in your model. Okay, so put a slightly different way, maybe so if you have a linear regression model, right? That might look something like this, right? So you have your dependent variable y there, and then you have an intercept, and that's beta 0 here, and then you have a number of predictors, which I've called x, and they all have their coefficients, right? These are the things we want to estimate. And then say we have another predictor, which is kind of special in this example, right, which I've called a. But it's, in reality, this is one of many predictors in our model. And now say there is multicollinearity between A and the other predictors. And specifically, to start out with, let's say that there's perfect collinearity, right? And that means that we can just express A as a linear combination of the other predictors, right? So instead of saying A, we could just say, A is of the weighted sum of the other predictors, A weighted sum. And okay, so that's kind of what it means. But okay. And clearly it's something that can happen, right? Because otherwise we wouldn't worry about it. But why does it happen? And kind of where does it come from? And I think it's useful to think of this as there being sort of two types of sources of multicollinearity. You can have multicollinearity that kind of occurs naturally, if you like, right? So you might have a number of measurements, a number of variables that measure related things, right? For example, if you work in psychology, you might be interested in things like depression and anxiety, and those are two sort of separate phenomena, but they are closely related. And so you will usually find that measures of depression and anxiety are correlated. And if you have potentially several different measures of depression and anxiety in your model, then there's likely to be quite a bit of multicollinearity, right? And that kind of happens because you measure related things in different ways. Sometimes we get multicollinearity in a more sort of artificial way, if you like, because we took the variables that we measured and we did something to them that makes them related to each other, right? So if you have measured people's weight and height, and you then compute BMI, then BMI is going to be kind of related to weight and height, right? Because that's how you computed it. So if you include all of those in the model, you might run into trouble. Another way this might happen is if you have a variable like age, and you are worried that there might be a non-linear effect of age, right? That's a fairly common thing to worry about. And one way to deal with that is to include sort of a squared term for age in the model as well, or can include higher order terms as well. But of course, age and age squared, they are correlated, right? They're based on the same data. And that might give you multicollinearity. And similar transformations of your data. If you're not careful, include all of them in your model. This will cause trouble. Okay. So it can happen, right? We've looked a bit at what it kind of is its definition, I guess, and where it might come from, but really what is worrying us is what it might do, right? What might it do to our results? What happens if there actually is multicollinearity, and why is it bad? And if you, I mean, you can, if you're worried about it, you can go and you can Google and you'll find lists of things that look somewhat like this. Right, so if there's multicollinearity, it will tell you that the size of your standard errors will increase. And we don't like that because your small standard errors are good. It gives you more precise estimates, right? That's what you want. So okay, that's not good. It also will make the estimates of the coefficients in the model unstable. And they will become very sensitive to the variables that you do include in the model. And that means that if you make slightly different choices about which variables you include in the model for whatever reasons, potentially unrelated to multicollinearity, you can get just vastly different answers, which could lead you to, well, your estimates will look very different, and your p-values may or may not be significant, significant in one case and not in the other. And that will lead you to different conclusions. And that's kind of worrying, right? Because making a small change to your model should not drastically change your conclusions. And so what I want to do for most of the rest of the talk is, well, I want to do two things. I want to look at what actually happens, right? What does multicollinearity look like, and what happens when it occurs? And then in the end, talk a little bit about what you might do about it, right? How can you handle the problem? But yeah, to do that, I think we need some data, right? So far, everything has been quite abstract, and that's not really very helpful. So I made up some data. It's very simple and artificial data, but the advantage is that we know what's going on, right? We know exactly which things are correlated with each other, and we can see, and we know what the answer should be, what the coefficients in our model should be, and we can see what happens to them as we do different things, okay? So the data I created looks like this, right? So there's one dependent variable, y, and there's 5 predictors with very simple and easy to remember coefficients. They just go from 0.1 to 0.5. And then, of course, there is some sort of normal noise that I added to this, right? And then I created another variable a, which is just a linear combination of these x's. And that's it. And so obviously, there's going to be multicollinearity there with a and the x's. And this is a little bit of the data. That's what it looks like. It doesn't really matter. And now I haven't told you how I've made up A, but actually, if you wanted to and you had the data, it would be easy to find out, right? Because A is just a linear combination of x1 to x5. So you could go and say fit a linear model, and it will tell you exactly the coefficients I chose for x1 and x1 to x5. I did this in R, and it warned me that there was a perfect fit. There were no residuals, and it was really upset about it. But it doesn't matter in this case, of course. Right? And yes, so that's this is what A is, right? So these go from 0.25 times x1 to 0.05 times x5 in your decrements of 0.05. All right, so let's see what happens. So what would happen here if I actually try to go and fit a model that includes all of these variables, x1 to x5 and a? What do you think might happen? Yeah. So the thing is, if I try to fit this model, this should not work, right? What does happen is, so if I did this in R, and this is what happens. There is no warning, but it will simply drop the last variable in your model because it realizes these are perfectly correlated. I can't estimate something for all of them, but I don't need all of them, so I just want to drop one and everything's going to be fine. Right, and so this is perfect multicollinearity. This is the thing that you most definitely can't have, right? Because if you have perfect multicollinearity, you can't fit the model. That's what the theory says, at least. In practice, it's not really a problem, right? Because you can fit the model if you just drop one variable. And if you drop one variable that's perfectly correlated with a subset of all the others, then you're still fine. All the information is there, right? So this you can do it. In this case, it's perfectly fine because A has no extra information, right? There's nothing there. We are not missing anything. And actually, if you look at the output, the estimates of the coefficients for the x's are pretty good, right? They should go from 0.1 to 0.5, and they mostly do. I mean, there's a little bit of noise, but so this is fine. Did a decent job despite me throwing A sort of as a wrench into the works. Fine. As a side note, if you do this in SPSS, it will do something similar, where it just drops one variable. It does not seem to be the last one. I couldn't quite figure out what its rules are as to which variable it drops, but it drops one and gives you, essentially equivalent output. So dropping one of these variables is fine, right? Nothing bad has really happened. All the information is still there, and our answer looks good, right? But it kind of does matter which one you drop, right? Because so here we dropped A, and that was because it happened to be last, and that was a great choice because A was entirely redundant, and the x's are probably what we should care about in this particular setting, right? But what if we want to have A in the model, right? That should be a valid choice. We can have A in the model, and we'll just drop one of the other variables. So I went and dropped x4. And then this is the output you get. R is perfectly happy. It will fit the model. There's no problem there. And so this is a valid answer to our problem of fitting a linear model to this data set. But it looks very different, right? These coefficients are not the coefficients we had before. So what's going on here? Of course, the first question you might have is, well, is this wrong, right? Did it somehow do something wrong here? Are these results wrong? And the answer is not really, right? So if you look at your fitted values, right, the sort of predictions for the model, if you like, and plot them against the observed ones, there's one model on one side and the other on the other, and these look the same, right? And they don't just look the same. If you overlay them, you see they're exactly the same. They're identical. So the answer, so the overall answer you get from these two models is the same. But if you look at the model output side by side, it doesn't look the same, right? And that's a problem. You can, if you like, convince yourself that these actually are the same. So if you write out how the model on the right here, that includes A, what that predicts for your dependent variable. And remembering how I defined A, you can kind of plug that in and you can then go and simplify it. And you will find that actually this is exactly the same, right? It's still telling you this is 0.1 times x1 plus 0.2 times x2. It's just expressed in a very awkward way because we kind of have to filter it through A, right? Because we didn't include x4, we included A instead, and then everything kind of gets scrambled around, so it still makes sense. But yes, these are basically the same, they just look different. Which is kind of fine if you just care about prediction, right? If you just want to take some data and predict what y is, whether you use the first model or the second one, it makes no difference whatsoever. You'll get the same answer, all is good, right? You can forget all about multicollinearity. You don't have to worry about it. But if you want to look at a table like this and interpret the estimates for the coefficients, you have a bit of a problem, because if you look at this table and I ask you, what's the effect of x1 on y, you're probably going to say something like, for each unit of increase in x1, y will decrease by 0.9 or so. Right? That's what you'd say. And that's not really right, because for each unit increase in x1, y will increase by 0.1. Right? So that's a bit misleading. And in this case, we, of course, could kind of sort it out with a little bit of trouble because we knew exactly what A is. But in practice, when you encounter multicollinearity, it will often be that these variables are naturally related in some way, but you don't know how exactly, right? So you can't do this thing where you sort of decode everything and get the right coefficients for all your x's back. You can only do that with artificial data like this. So this is really what the problem is, right? The problem is that with multicollinearity in your system, the coefficients can be pretty wild and misleading, and you have to be super careful how you might interpret them. So yeah, so that doesn't sound so good, right? This is most definitely something we would like to avoid. So the question is what to do, right? So you have some data and you think there might be multicollinearity and you have to deal with it, right? So the first thing, of course, is you need to be aware of the problem. And so what we'll do is we look at ways to diagnose multicollinearity. And then knowing it's there, well, that's all well and good, but you still have to do something about it, right? You're not just going to abandon your project there because there was multicollinearity. You want some solution. And the bad news is that there isn't really a perfect solution. The good news is that maybe sometimes you can do something, that's not too bad. All right. So how do you quantify multicollinearity? How do you measure it to know that it's a problem? Well, if you remember at the beginning of the talk, ages ago, there was this thing on the screen for a little while, where I said, multicollinearity, it means that there is sort of a linear combination of predictors that is correlated to another one. And I showed you how that's basically a linear model, right? And Well, we can fit linear models like this for all our predictors, right? That's easy enough to do. Well, it can be a bit tedious if you have to do it by hand, but your computer will do it for you. It's fine. So we can fit those models, and then each model will come with an R-squared value, right? That will kind of tell you about how much variance from of this predictor is explained by the other predictors in the model. And you can probably see how this will start to tell you about the presence of multicollinearity. And then similarly, so you can think of 1 minus that R-squared value as the sort of unique variance in that predictor. And in our example with A and the axis, that obviously was 0, which is why R freaks out a bit. And then what we do is you take kind of 1 over 1 minus that R squared, and we call that the variance inflation factor, which is commonly used as a measure of multicollinearity. And it's called the variance inflation factor because this is how much the size of your standard errors increases in the presence of the multicollinearity as opposed to the same model without multicollinearity. And I promised you that your computer will do these computations for you. And so here are some ways in which you can do that. If you work in R, there's the VIF function in the car package, or the OLS VIF toll function in the OLSRR package that will do compute variance inflation factors for you. In SPSS, there's an option you can provide to the regression function, and similarly, Starter has an option. And if you do this, you'll get a number. It will output one number for each predictor in your model, and the higher that is, the more collinearity there is. Typically, so values above 5 and certainly above 10 are considered to be high. And if your VIF is above those, then that's generally considered a sign that there is enough multicollinearity that you need to do something about it. As always, with sort of root of sum, you should be careful. It's not like if your variance inflation factor is 5, everything is horrible, and if it's 4.9, everything is great, right? So, but look at these as a indication of how bad the situation is and how urgently you need to deal with it, and how careful you need to be in interpreting your coefficients. If everything is fine, it should be 1, right? So because then that means that the R squared from the model where you for your regression of that predictor against all the other ones, then it was 0. So here's an example of doing that in R, and here the function I used produced a table for that model that includes x1, x2, x3, x5, and A that we looked at before. And you can see it says there is multicollinearity. There's a lot of it for A, as you would expect, and varying amounts for the other vowels. All right, so it's sort of informative, but it doesn't quite tell you what to do with it, right? It tells you there might be a problem. A might be a problem. X1 might be a problem. Maybe X2 is a problem too, who knows? So what do? Well, I promised you some possible solutions, so let's try and talk about them and see whether they're any good. So the first option that might occur to you is, well, if there's a variable with lots of multicollinearity and my VF is really high, I just going to remove it from the model, and that might solve the problem, right? And that is indeed a common strategy, I think. So here are our VRFs again as a reminder. So A was 15.5 and by far the highest. So we're just going to drop that from the model, right? And this is what happens. I don't know whether you can read it. It's quite small, unfortunately. But so on the left-hand side here, we have a model, the model that we had before. And then on the right-hand side, the model we get after I removed A. And then, the variance inflation factors for the remaining variables, they're all fine, as you'd expect, because these are indeed, independent. Now, okay, that's good, I guess. The estimates for the coefficients for the variables that do remain in the model are actually not too far off what they should be, so that's kind of encouraging. But we are missing information now, right? We've excluded A, and A was our only source of information about X4. So now we no longer know about X4, right? So what we get is a model that fits our data not as well as it did before, because in removing A, we removed some information that would have been good to know about. Otherwise, this model is kind of fine, I guess. And if you can afford losing that information, maybe this is the lesser of two evils. But be aware that when you remove vowels, you probably remove some information, and that may hurt you in other ways. And I mean, how bad that is kind of depends on how many vowels you need to remove and how many so how much extra information was in those vowels. Yeah.
What if I need to default A?
Yes. So if you need to control for A, obviously you can't remove it, right? Then if you go back at this and you say, well, A looks bad, but I have to keep it, so I'm going to try and remove X1, right? In this particular case, what would happen is that you remove all the X's and you're just left with A, right? Because A, in this case, happens to include all the information that you need anyway. But in reality, that's not likely to happen. But so, if you can't remove the most offending variable, you remove some others. You might have to remove more variables, but and you may or may not end up with a model that's still useful. And that's kind of where we get to the point of there is no perfect solutions. Now you could say, well, yeah, my predictors, they are all kind of correlated and weird. I just want to make them independent of each other. I don't want them to be correlated, but I want to keep all the information, or as much of the information as I can. I'm going to do something like PCA. That will give me a new set of predictors, and those are guaranteed to be uncorrelated. That's great. So no multicollinearity. And I mean, you can do that easy enough. And you can fit a new model that now the model has your principal components as predictors rather than your original variables. And there's no multicollinearity. So these coefficients, they're fine. The problem is, well, you have no idea what I mean. It's really hard to interpret these principal components. Right? If you want to make sense of is if you want to know about some relationship between your predictors and your dependent variable, this is not going to tell you, because your principal components are, well, each one of them is a linear combination of all your predictors, right? So basically, you've gone from a situation, well, in this example, you've gone from a situation where you have your individual variables and then a variable that's a linear combination of those, to a situation where all the variables are linear combinations of your original variables, and understanding what's going on at the level of the individual variables basically becomes impossible, right? Sometimes you get lucky and you have sort of maybe groups of related variables that end up being these sort of main factors in one of the principal components, and you can say, well, principal component 2, that's mostly like physical fitness or something, right? And that's fine when that happens, and then it can be useful. But in general, it's kind of difficult. It's not really allowing you to interpret anything. I should have shown you this earlier, but yeah, these are the principal components in this example. And you can, I mean, the advantage is you know what you're getting, right? You know that what the predictors in your model are these linear combinations of your original variables. But yeah, in most cases, then looking at these and making sense of it, it's not really practical. If you are interested in going down this sort of route, you probably want to look at partial least squares, is what the method is called. And it can be helpful in some cases, but yeah, it's a bit problematic making sense of it. Now, you could also say, well, I don't really want to bother with all these choices. I just want to fit a model that I can, somewhat trust without having to arbitrarily choose which variables to exclude and that sort of thing. So I want to, the regression should kind of take care of it for me. And then maybe penalized regression is for you, which kind of does something magic, because it allows you to take all your variables, x1 to x5 and a, that you remember when I tried to fit that model, a just got dropped, or some other variable might get dropped. But with penalized regression, you can take all of them and it will deal with it in a way that you can maybe kind of make sense of. So of course, it will not be able to give you your estimates for the coefficients of all of the variables, because that's just not possible. But it can help you figure out which variable you might want to drop, basically. And it won't depend on the order of the variables or anything like that. So it's not as arbitrary, I guess. And it will try to do it in a way so you get a good model fit, basically. This is what happened when I tried to do it. You see that x1 got dropped, and a is still in there. But so this works. I can fit this model. I don't have to worry about it too much. But again, interpreting these coefficients is a little bit difficult, and it's made more difficult by the fact that they're now biased, because all the coefficients kind of get pushed towards 0. So they're smaller than they ought to be. And when you want to interpret this in some sort of real world context, right, then having a coefficient that is not quite right is a bit problematic. But you can fit a model, so there's something. And this incidentally is also useful if you maybe have more variables than you actually want to include in the model, right? So if there's also some sort of variable selection you need to do, penalized regression will also do that for you, so you can get all in one go if you like. But it's, yeah, again, not a perfect solution, but good in some cases. Now, I have one more option for you, one more imperfect option. So you could say, well, I have this variable that is clearly correlated, with some combination of the others. And that's a problem, but I don't want to throw this variable away because there's information there that I need, to make sense of my data. Like, what if it's age? And so you could say, well, we can figure out how this variable relates to the other variables, right? Because we can fit a linear regression that captures this linear relationship that's causing us trouble. And that's, in fact, exactly what we do when computing the variance inflation factor. So we could fit this model. And now the model tells us which part of A, say, is explained by the other variables, right? And so with this model, we could take the part of A that's explained by our other predictors and just throw it away because that's in our model already, right? We don't really need this again. And we'll just keep the bit that's left over. So in our regression model here, that's the residuals. And I think you might want to keep the intercept too. And so these are the parts of A that aren't really explained by your other predictors. And you can take that and include that in your model instead of A, which I've done here. So I think in this case, on the left-hand side is just the regression I did for A. And on the right-hand side is the resulting model that we actually care about. And that kind of works. Right? So this allows me to fit a model that includes at least parts of all the variables. That's kind of nice. It also, I think it turned out here that the coefficients for x1 to x5 are actually I say all our values, right? So this doesn't include x4, right? But because here I should have maybe pointed this out earlier as to not confuse you unduly. But here I'm kind of pretending like we're in a situation where we don't have perfect multicollinearity, right? We're in the more common situation where there's multicollinearity, but it's not perfect. And so basically we don't have independent information on x. So, but the coefficients for x1 to x5, excluding x4, are the same, I think, that I got from the model that had just those values in it and no A. But that model had a much larger intercept. The intercept there was 4 or something. And now the intercept is near 0, as it should be. And instead, the leftover part of A is picking up the slack that x4 left. And if you think about why is the coefficient for that 4, it's because the contribution of x4 to y was 0.4. The true coefficient of x4 is 0.4, but the coefficient of x4 in A is 0.1. So A only has 1/4 of the amount of x4 that needs to go into y. So the coefficient is 4. So it did the right thing. And so this can be useful, I think. It does have its limits. So it works reasonably well when you have one variable that you need to deal with. If you have multiple ones, it quickly becomes kind of difficult. And you have to be still quite careful in interpreting this, because it's tempting to think about this entry there that relates to A as if it were A, but that's not true, right? It's the part of A that's not explained by the other predictors in the model. And in practice, you probably don't know what that actually is, right? So again, you end up with a variable in your model that you don't quite know what to make of. And that's okay in some cases, right? So if it's age that you need to control for, but that you have no interest in interpreting anyway, then maybe this is okay.
I just think you control. Taking out all the correlated bits twice.
Yeah, I don't know whether you can. Well, you're not controlling for age directly. I think you're right. And in fact, as you've seen with what I said before, the estimates of the other vowels are as if what they would have been if you hadn't controlled for age, right? So let's do, yeah, so don't do this when you want to control for age, I guess. Yeah, exactly. So the other vowels, if this was age, the other vowels are kind of what they would be if you, so they're not age controlled estimates, right? But if, yeah, so you do get an estimate for X4, I guess is what you're getting, right? And of course, in this case, well, the way this is set up is not quite the way age would be, I guess, because age isn't really, the aggregate of just everything else. But so you've basically pushed the parts of A that are related to the other predictors to those predictors, right? And then you have something that can pick up the slack of whatever was left over, so you don't lose that information. But you can't really do much with that information because you probably don't know what it is. So age was a bad example, I think. It might be more useful if you have something like, I don't know, it might work with something like depression and anxiety. If you want one variable that captures, everything that is related to depression and anxiety, and one that's kind of, one that is, say, all of depression and the part of anxiety that is directly related to depression, and one variable that is, anxiety stuff that's not depression related, right? So you can kind of partition it that way. And in that case, maybe you can interpret it, but it's still kind of tricky, right? So it gets messy, and if you have more than one of these, it gets really messy really quickly. So yeah, it's a little bit problematic. And I think all of these solutions can be useful under the right circumstances, but you have to be very careful about which one you pick in a specific case, because it might not do the right thing for you in that situation. And in all of these cases, you have to be quite careful about how you then interpret your coefficients and what it all means. So you can't really get rid of that. You can help things a little bit, right? So there's this type of multicollinearity that you introduce somewhat artificially by doing some sort of computing on your vowels first, and then maybe including several of them. So be careful what you do there, I guess. And yes.
A person has a question.
Yes, please.
How do you handle multicollinearity and logistic regression?
Well, the same way, basically. I think the general idea is the same. It's just as troublesome, and But similar principles apply. I mean, you can do the same things. But it's just as bad. The only good news is that when you're doing logistic regression, you're slightly more likely to be interested in prediction. And if that's the case, then you don't have to worry.
I will also say that I ran into that particular problem in SPSS, and if you're in the logistic regression command area, there is no way to ask for collinearity diagnostics. So you have to sort of fudge around the linear regression stuff if you want to find out what your variance place factors and tolerances are.
Yes. Well, I mean, I should maybe say that with all of this, and I think we can probably just move on to questions, that with all of this, I've assumed that you're in a sort of situation where doing these things makes sense, right? Like fitting the variance inflation factor with fitting those regressions. That assumes that that's a sensible thing to do for the predictors you have, right? Even if you're fitting a linear regression, not a logistic regression, you might have binary predictors, right? In which case it doesn't work quite like that in a sensible way. So that is something you have to be aware of. This was a sort of easy setup because multicollinearity is difficult enough by itself. Yeah, there was something else I was just thinking of, but now it has slipped my mind. Are there any more questions? No? Then I guess our little banana person says happy holidays. And this was the last seminar for the year, I think. And we'll be back next year with more exciting stats.
Thank you.